Before the electric motor changed everything, every machine in the factory ran off one shaft above the workers' heads, with leather belts and chain drives dropping to every lathe and press and drill and saw below, all of it spinning at speed with nothing between moving parts and the people working among them. If your sleeve caught the wrong belt, you didn't pull free, but the belt didn't know the difference between a sleeve and an arm. 2,000 feet per minute. Your nervous system needed a full second to register the contact. The belt needed a tenth of that. If you're new to Steel and Sweat, this channel covers the machines and the men of American industrial history, the things that built the country and the things those things cost. Subscribe and leave a comment with the next story you want us to dig into. To understand why the line shaft factory was so consistently lethal, you have to understand how it worked. Because the engineering logic of the system was sound and the mechanical execution was elegant, and neither of those things had anything to do with what happened to the workers inside it. The line shaft was exactly what it sounds like. A steel shaft, typically 2 to 4 inches in diameter, running horizontally the full length of a factory building, suspended from the ceiling on bearing mounts, spaced every 8 to 12 feet. At one end, the shaft connected to the power source, or a steam engine or a water wheel, or in later installations, an electric motor driving the shaft as a unit. When the engine ran, the shaft turned, and it turned continuously at whatever RPM the engine and pulley ratio produced, typically between 150 and 300 revolutions per minute for the main shaft, all day, every operating day of the week. The machines on the floor below the shaft were each connected to it by a flat leather belt looped over a pulley on the line shaft above and a pulley on the machine below. The machine's operating speed was determined by the ratio of those two pulleys. A small pulley on the line shaft driving a large pulley on the machine produced slow, high torque motion. A large pulley on the shaft driving a small pulley on the machine produced fast, low torque motion. In a complex factory, dozens of these belt connections ran from a single line shaft simultaneously, each one tuned for the specific speed requirement of its machine. A large factory might have multiple parallel line shafts on different levels, interconnected by their own belt drives, with secondary countershafts branching off the main line shaft to reach machines farther from the center run. The chain drives came into the system where belt drives were inadequate. Leather belts slipped under heavy loads and stretched over time, producing speed variation that was unacceptable for certain operations. Roller chain drives, the same mechanical principle as a bicycle chain, scaled up to industrial proportions, transmitted power with a fixed ratio regardless of load. A chain drive connecting two sprockets did not slip, did not stretch significantly, and could transmit far more torque per unit of width than a leather belt. But it ran under considerable tension, and that tension had consequences when something went wrong. And what the line shaft system produced on a running factory floor was a space filled from ceiling to floor with moving elements. The main shaft turning above the workers' heads, the belts dropping from the shaft to the machines, dozens of them, each one moving at its operational speed in a vertical plane between the shaft and the machine below. The machines themselves turning, reciprocating, pressing, and the workers positioned among all of this to operate the machines, load them, adjust them, clear jams, and move between workstations. In a factory built in the 1880s or 1890s, the spacing between machines was determined by the machine's operational requirements and the belt geometry, not by any consideration of the space a human body needed to move safely through the facility. The workers fit into the space that was left after the machines, and their drive systems were positioned. A belt running at operational speed carries kinetic energy in proportion to its weight and the square of its velocity. A 6-inch leather belt running at 1,800 feet per minute is transmitting approximately 15 horsepower and maintaining several hundred pounds of tension between its tight and slack sides. At that speed, the belt is moving at 30 feet per second. If that belt contacts a loose element of a worker's clothing at the running nip point, the point where the belt meets the pulley and the two surfaces converge, the physics that follow are not a matter of strength or reaction time. They are a matter of geometry and velocity. The running nip point was the specific geometry that killed. Where a flat belt approaches a rotating pulley, the belt and the pulley surface converge in a wedge shape that narrows to 0 at the contact line. Any material drawn into that wedge is pulled toward the contact line by the motion of the belt. If the material is loose cloth, it compresses and follows the belt around the pulley. If the material is attached to a human body, the body follows. The force pulling the material inward is proportional to the belt tension, which runs to hundreds of pounds. The speed at which the material is drawn in is the speed of the belt surface, which is measured in thousands of feet per minute. The human reflex arc, the time between the nervous system registering a stimulus and the muscles completing a response, is approximately 150 to 200 milliseconds. At 1,800 feet per minute, the belt travels 45 feet in that time. There was no pulling free. The phrase appears in factory inspection reports and survivor accounts from the period with a frequency that reflects how completely the physics refused the possibility. Workers who survived contact with a running belt survived because the cloth tore before the body did, or because someone near the machine reached the emergency stop in time, or because the belt threw them clear before the wrapping completed. Workers who were not so positioned did not survive in the same condition they had arrived in that morning. The people who worked on these floors were not a single workforce in any meaningful demographic sense. American manufacturing in the belt drive era employed men and women across a wide range of industries, and the specific composition of any given factory's workforce reflected the industry, the region, and the period. Textile mills in Massachusetts and Rhode Island employed predominantly women and children alongside men, some of the children as young as 10 years old in the pre-regulation era, all of them working in proximity to the same belt systems. Machine shops and metalworking facilities in Ohio and Pennsylvania employed predominantly men, many of them recent immigrants from Eastern and Southern Europe, who had arrived in American industrial cities through the same labor networks that fed the steel mills. Shoe factories in New England, furniture factories in the Midwest, paper mills across the Northeast, all of them different goods and different workers running on the same overhead shaft and the same belts. The children were a particular category in the injury statistics, documented separately in states with child labor reporting requirements, and folded into the general machinery figures in states without them. A child of 12 or 13 working a belt-driven machine had the same exposure to the nip point hazard as an adult, and less of the accumulated floor awareness that an experienced adult worker developed over time. The factory inspection reports from Illinois and Pennsylvania in the 1890s contain accounts of children injured by belt drives that are among the most specific and clinical documents in the accident literature of the period, because the inspectors writing them were attempting to build the evidentiary record for legislative reform and require detail to make the case. The detail they recorded is exact. The economics of guarding resistance were straightforward, and the industry understood them clearly. A wooden or sheet metal guard fitted around a belt nip point cost money to fabricate and install. It reduced access to the belt for adjustment and tensioning, adding time to maintenance operations. In some configurations, it created an additional hazard of its own if poorly designed, catching tools or debris. These were real costs and real operational complications. And the factory owners and engineers who cited them when resisting guarding requirements were not inventing objections. But the cost of a guarded factory was a fixed and knowable number. The cost of an unguarded factory was distributed across the workers in the form of injuries and deaths, and, in the period before workers' compensation laws, the direct financial cost to the employer of each injury was low. A worker injured and unable to continue was simply replaced. The legal liability under the prevailing assumption of risk doctrine required the injured worker or their family to prove negligence in court, a process that was expensive, slow, and frequently unsuccessful, especially when the worker was an immigrant with limited English and no money for legal representation. The factory owner's calculation was not a moral calculation. It was an economic one, and the economics favored leaving the belts unguarded. The documented injury patterns from the belt drive era appear in the factory inspection records of the period, with a specificity that reflects the consistency of the mechanism. State labor bureaus in Pennsylvania, Ohio, Wisconsin, and Illinois produced annual reports on factory accidents through the 1890s and 1900s. And the machinery category within those reports shows a pattern stable enough across years and facilities to be read as a description of the system, rather than a collection of individual misfortunes. Degloving injuries to the hand and forearm, where the skin and soft tissue were separated from the underlying structures by the shearing action of a belt nip point, appeared consistently. Avulsion injuries to the shoulder and upper arm, where the limb was pulled against the belt's direction and the joint was forced beyond its structural limits, appeared consistently. Scalping injuries, where a worker's hair caught in an overhead belt and was drawn upward faster than the skull could follow, appeared consistently enough in Wisconsin's factory inspection reports from 1905 through 1912 to constitute their own statistical category. The word scalping in those reports is clinical. It describes what the mechanism produced. The Wisconsin Inspection Division documented that in the facilities it surveyed, more than 60% of serious machinery injuries were attributable to unguarded belt and chain drives. These were not isolated findings. The pattern that Wisconsin documented was replicated in the inspection reports of every state with an active factory inspection program. The specific percentages varied by industry sector and facility type. But the category that belt and chain drives occupied in the injury statistics was consistently the largest single machinery-related category across all of them. The system that produced the goods also produced the injuries, in proportions that the inspectors who counted them found impossible to characterize as anything other than structural. If you're finding this history as gripping as anything we've covered on this channel, go ahead and hit subscribe right now and drop a comment below with the next industrial story you want to see. But the chain drive failures produced a different injury pattern entirely, because the failure mode was different. A leather belt that caught a worker drew the worker into the nip point continuously at belt speed until something stopped the process. A chain drive under load that failed catastrophically, that shed a link or threw a chain off a sprocket under full operating tension, did not catch and draw. It released. The stored elastic energy in a chain under several hundred pounds of tension, freed instantaneously when the chain broke, produced a projectile effect. A 40-link section of 1-inch roller chain, released at operational speed in an industrial chain drive, had the kinetic energy of a thrown weapon. The direction it went was determined by the geometry of the failure, and the geometry of the failure was not predictable. The specific trajectory of a thrown chain depended on which link failed, where in the rotation cycle the failure occurred, and the geometry of the enclosing structure around the drive. In a factory floor of the period, where chain drives ran in open air between sprockets with no enclosure, there was no structure to contain the release section. A chain thrown from a drive running at industrial load speeds could travel across a room. Well, the weight of the chain multiplied by its velocity produced impact force at the end of that travel that could break bone, collapse a rib cage, or fracture a skull. Workers who were struck by thrown chain in documented incidents in American factories were sometimes found at a distance from the drive that had failed, the trajectory of the chain readable in the distance and direction from the machine. The industry's response to thrown chain hazards was enclosure, where it was adopted at all. A chain drive running inside a sheet metal housing could not throw its chain into the open floor. But enclosure added cost, reduced access for inspection and lubrication, and in facilities where the maintenance philosophy was to run the drives until they failed and repair them, the chain enclosure that would have contained the failure was the same enclosure that made monitoring the drive's condition more difficult. The facilities that enclosed their chain drives were the facilities that had already decided that the maintenance cost of monitoring was worth paying. The facilities that had not made that decision were the ones producing the injury statistics. Factory workers in the chain drive era understood this hazard. In the same way, workers in every dangerous industrial environment developed practical knowledge of what the machines around them could do. They knew which chain drives were running hot, which sprockets were worn, which drives had been throwing chain, and they positioned themselves relative to the machines the way a person navigates any space containing intermittent hazards, aware of the current state, prepared to move, and accepting that the knowledge was imperfect and the preparation was limited. But knowing that a chain might throw did not tell you which direction it would go. The knowledge reduced the probability of being in the worst possible position. It did not eliminate the possibility of being in a bad one. Could you imagine working every day in a room where dozens of leather belts were running above your head, all of them moving at speed, all of them within reach of your clothing if you stepped in the wrong direction, and none of them with a guard between them and you? That was the standard operating environment of American manufacturing for the better part of 60 years. The factory design decisions that produced this environment were not made carelessly. They were made by engineers and mill owners who understood the mechanical system very well and were optimizing it for the production goals it existed to serve. Keeping machines close to the line shaft overhead minimized belt length and reduced the power loss from belt slippage and bearing friction. Keeping machines close together on the floor maximized the productive use of floor space in a building that had a fixed footprint. Both of these decisions were correct from the perspective of mechanical efficiency and capital utilization. Both of them created a floor environment where workers moved continuously through a field of exposed moving machinery with minimal clearance in any direction. The guarding that would have separated the workers from the drive systems was not absent because no one had thought of it. Wooden belt guards, sheet metal enclosures around nip points, and overhead guards that kept workers' bodies clear of the line shaft had all been described and in some cases implemented in forward-looking facilities by the 1890s. The technology was not complicated, but guarding cost money, required installation time, sometimes reduced access to the machine for adjustment and maintenance, and in the factory economics of the period, those costs were weighed against an injury rate that the industry had internalized as the normal cost of production, rather than as a preventable loss. The National Safety Council's 1913 survey of American manufacturing facilities found belt and chain drive injuries in the top 3 causes of factory fatalities nationally, alongside falling objects and caught in machinery incidents that were themselves often belt-related. The survey documented that the majority of the facilities surveyed had no systematic guarding program, and that the states with the most developed factory inspection systems, Wisconsin, Ohio, and Illinois among them, had achieved meaningful reductions in injury rates primarily through inspection-driven pressure on individual facilities rather than through any uniform national standard. The first meaningful American standard for machine guarding, developed through the American Society of Safety Engineers, was not widely adopted until the 1910s. And its enforcement depended on state factory inspection programs that varied dramatically in funding, staffing, and legal authority. Well, a large factory in a state with an active inspection program and an engaged inspector operated differently from an identical facility in a state where the inspection division had 3 inspectors covering the entire manufacturing sector. The standard existed. The mechanism for enforcing it did not exist uniformly. And the gap between the standard and its enforcement was measured in the injury statistics of the states that fell on either side of it. The men and women who worked the belt drive factory floor developed their own practices for surviving an environment that the formal safety apparatus was not adequately addressing. They wore tight-fitting clothing where they could obtain it. They kept their hair short or confined. They learned the timing of the machines around them well enough to move through the spaces between them at moments when the risk was lower. They watched each other in the way workers in dangerous environments watch each other, not always consciously, but with the baseline awareness that comes from spending enough hours in a space where attention to the other person's position is part of knowing what the space is doing. These practices reduced injury rates. They did not reduce them to the level that guarding would have produced, because they required continuous vigilance from people who were also performing precision work at production speed. And continuous vigilance at that level is not sustainable across a 10-hour shift 6 days a week. The transition away from line shaft and chain drive systems came through a technology that made the entire architecture obsolete rather than reforming it. The individual electric motor, affordable and reliable enough for widespread factory use by the 1910s and 1920s, allowed each machine on the floor to have its own power source, eliminating the line shaft overhead, the belts connecting shaft to machine, and the constant presence of exposed drive systems throughout the working space. A factory built around individual motor drives had no line shaft. It had no overhead belts. The chain drives that remained were contained within machine enclosures, rather than exposed in the open air of the production floor. The injury mechanism that had produced 60% of serious machinery injuries in inspected Wisconsin facilities did not improve incrementally. It was removed. The transition was not instantaneous. Many American factories ran line shaft systems well into the 1930s, and in smaller facilities and specialty operations, elements of the old system persisted longer than that. But the direction of the transition was clear by 1915, and the mills and factories that modernized their drive systems in the 1920s found that the injury rates associated with belt and chain drives dropped to near zero in the converted facilities. Not because the workers had changed, but because the hazard had been engineered out of the space. The workers who spent their careers in the belt drive era, the machinists and press operators and mill hands who worked their entire working lives in the line shaft factory, did so in an environment that the industry's own safety surveys consistently identified as preventably lethal. The guarding technology existed. The engineering understanding of the hazard was documented. The injury statistics that measured the cost were recorded annually in state labor bureau reports that anyone in the industry could read. What was absent was the combination of regulatory pressure, economic incentive, and managerial priority that would have moved guarding from a forward-looking practice to a universal one. In the gap between knowing and doing, the belt drive factory accumulated its statistics, category by category, year by year, in the same clinical language the labor bureaus required for their tables. The shaft is still. The belts are gone. But in the 50 or 60 years before that stillness arrived, the line shaft factory produced goods at a scale and pace that built the material foundation of the modern American economy. The textile mills clothed the country. The machine shops made the components that the railroads and the construction industry and the consumer goods manufacturers required. The furniture factories and the shoe factories and the paper mills filled the markets that a growing industrial nation created. All of that production came out of the belt drive factory. And the belt drive factory ran its production through a workforce that absorbed injuries at a rate the industry's own surveys described as preventable, in a regulatory environment that moved toward prevention more slowly than the injury statistics justified. The shaft is still. The factories where they ran have mostly been demolished or converted, are in the space where a worker once moved carefully through a field of spinning leather and chain has been replaced by something quieter and safer and completely unrecognizable as the same kind of place. But the men and women who worked in it were real, and the injuries that the system produced were real, and the knowledge that the guarding technology to prevent most of those injuries existed and was not applied is also real. The bureau tables recorded the outcomes without recording the names. That is what those columns of numbers represent, the cost of the gap, paid in the currency the gap required, by the people who had no alternative but to pay it.